Here's another picture. Here's an xk. If I pick 2 points, y and x, x has to be in one of the intervals I've defined here, right? I'm going to put this is the ghost interval. This is the full delta, right? This is the delta over 2. Remember how we did that on purpose? So the intervals I've created, of which there are finitely many required to come and set, are the ones with the hard brackets here. If I pick 2 points, x and y, x has to be in one of these, right? I mean, everybody got to be somewhere. So x has to be in one of them. Now y could be some horrible other place, way far away. I would like to pull y into this interval. Okay? Now I can't pull them all the way inside the hard interval. I'm going to pull them inside the dotted interval. How am I going to do that? I'm going to define delta of epsilon to be the min. The min over all the k's of the delta epsilon over 2 x sub k's. Remember these guys? Those were the deltas that were figured out for every x. Well, k of the x's are now distinguished points, the centers of these little intervals. So I got those. So I go find their deltas that we had already calculated, right? We had continuity at every one of these, and that's where the delta came from there. So this delta is the full distance out here at xk. Half the delta is this one. All right.
So it doesn't hold the bench. Are you trying to?
No.
Why do you find a finite percent?
I find a number, but it seems like because you're trying to approach something that really doesn't exist.
No, these all exist.
A point is infinitely small. Right?
Yeah, I'm just surrounding it, that's all.
But doesn't it keep getting smaller?
No. No, don't need. No, I can't let these things get too small because I have to cover the set. Well, you know, AB could be the interval from -1 to +3. And the xk's could be, say, every 8th point in between. So I need a reasonably fat interval here to cover, centered in each one of those special points to cover everything.
But it still seems like you're using the center.
I don't know if you let it shrink down.
It seems like you're trying to grab that infinity thing.
No, I'm not. I have to cover everything. And that prevents me from getting too small.
If you look at large number of i's and k's.
One of the things that is difficult to get in analysis is the epsilon delta part. It's a conditional part. Epsilon can be quite large. What you have to do is come up with a delta that works with the given epsilon. Now, if epsilon is quite small, and you can still come up with a delta for however large epsilon is always greater than 0, so it doesn't go away. Then all these properties happen. So it's vague in the sense of, well, how big is epsilon? Well, it's bigger than 0. Point is, it can be any size bigger than 0. If you philosophically, in principle, can find a companion delta, that once these guys are within delta, these guys are within epsilon, that activates continuity, uniform continuity, a bunch of stuff. There's a philosophical component to that. All right, so I've cut this down to 1/2 of the deltas. Remember, this was the full delta, so now this is delta over 2. Okay, so the delta of epsilon that I'm proposing is the correct delta for use in defining uniform continuity is this. This is a finite number of things. It's a list I go through. Find the smallest. Got it. Take half of that. Got it. That's my delta of epsilon. Okay? So now, if y minus x is less than the magic newly defined delta of epsilon, in this drawing, if this is where x occurs, where is the worst place that y could occur? Could y be outside the dotted lines? Remember, this thing is the distance from here to here. If x is inside the core, y has to be, worst case, sort of hanging on the edge out here, right? Okay? So if x is inside, y is inside the dashed line. But remember, what is the criterion? If you're within the dotted ones, 2 points within the dotted ones, the variation of the function then is within epsilon over 2. Right? Okay. So now, focus on these 3 points, xk, x, and y. The distance between fy and fx is equal to the distance between fy, f and xk, f and xk, f of x. True? This is that usual little annoying trick where we add and subtract the same thing. Okay? Now the triangle inequality, which we proved the other day. What's the triangle inequality say about this? It's less than or equal to true enough? Here, I'll even write this one over again so we can emphasize it. Okay, I think I can see the light at the end of the tunnel. True enough? The difference in function values, remember, here's the drawing again. The difference in the absolute difference in the function value here and here is less than or equal to the sum of the absolute difference between here and here and here and here, right? That's what this line says, the last line says.
Is that minus f of x that the very next time?
Minus f of x, right? Minus f of x, same thing.
And we put star.
Oh, I'm sorry.
Oh, sorry.
You have stars in your eyes.
Actually, what contact thought of.
Oh, that makes 2 of us. All right. Okay. Are we accepting of this? Is that okay, Matt?
Right.
You on board here, Lily? Everything's okay? All right. So now, what do we say? How big can this be?
Epsilon 2.
Remember where you are here. You're over here. You're comparing the absolute difference between the function here and here. You're inside the walls of the dotted lines there. That means the function variation absolutely could not be any greater than epsilon over 2. Likewise for here and here. So I have 2 epsilons over 2, which is epsilon. So what have we said here? F of y minus f of x is less than or equal to, actually, yeah, that's good enough, less than or equal to epsilon.
So now you have
So suddenly, out of the blue comes uniform continuity. So now what we can do is all of our partitioning with some confidence that we can control the errors on our rectangle estimates. If we don't have this, we can't do that. We can be like Cauchy and say, wave our hands and say it is intuitively obvious to the most casual observer that the error is controllably small, provided we make the partition elements very close together, right? So the subintervals are very small, the mesh goes to 0. But now we can do it efficiently. The Riemann and Cauchy integrals, and Stieltjes integrals as well, rely on Hein's theorem for this purpose, to control the error estimate you get on either side of the function. Okay? All right. Any questions on Hein's theorem? Okay. There's another way you can do this. This would be a good research project for somebody.